isotropy and geometry, and will be presented by Christoph Gorski from the JPL.
Thank you. Let me start with a disclaimer. The data is Planck. The subject is looking at things that are fundamental, however, touching on some issues that has seen division of opinions. If any opinions I express are disagreeable to anyone, I'm solely responsible for that. And now let me start slightly silly. So, mirror, mirror on the wall, who's the roundest one of all? My erudition wasn't as deep as to know that, so I went to internet and I found this. People are making balls for gravity probe B for attempt to replace the standard of 1 kilogram. The roundness specifications are in 10 to minus 7 relative territory. It's great. It translates to really small hills on the surface of the Earth. So humanity 1, universe 0 on that one, if you see what I mean. We have to get to polarization and measurements of deviations of that sort. We're not there. Temperature is a larger effect than that. We can make something we can take in our hand that actually is smoother than the universe at large scales. So now, end of the silly. The talk is mostly a highlight set for a couple of papers that were sent out on the data release. One is on isotropy and statistics of the CMB. The other is on background geometry and topology of the universe. So I will explain in a minute how things like that were done. Let me recognize Enrique, our chairman, Tony Banday, Andrew Jaffe, who's not here, Patricio Vielva. These were the guys who helped a lot pushing these papers through. Of course, on top of the very large group of people in non-Gaussianity working group that contributed over years to that. The synopsis of this talk is here, isotropy and statistics project has been originally undertaken to simply lay foundation for power spectrum analysis, to establish to what level are we comfortable doing two-point statistics as principal vehicle towards extracting science from Planck sky maps. In the process, we split efforts. There will be quite a few presentations in the next couple of days on various aspects of this, and I will mention some as I go through this. The first paper I mentioned has essentially done non-parametric suite of assessments of non-Gaussianity, came up to the conclusion that mostly things are not looking very non-Gaussian. These results are further strengthened by model attempts to limit non-Gaussianity described elsewhere in another paper. And isotropy part partially was motivated by following the WMAP discussion, WMAP stimulated discussion, where literature has been growing on the subject of looking at the maps and morphologically analyzing them and claiming deviations from the simple picture that was expected pretty much in the context of mostly inflation-inspired view of cosmology at large scales. Planck was interesting in that regard because due to its much larger foreground mitigation capability due to a larger number of frequencies measured with high accuracy, it was thought as a venue towards mitigating one of the objections that led to skepticism in the discussion of WMAP results, mainly foreground issues. And in general, of course, being another satellite mission, provide complete systematic redundancy given different nature of the instrument. So these are the pluses, somewhat surprisingly to some, although it's not really surprising because obviously we didn't expect WMAP to have performed wrong measurements. We find out Planck and WMAP overall very nicely consistent at large and intermediate scales, and this is where these effects reside. So some of these anomalies prove quite resilient and leave us with questions which can be taken from a big perspective. I will try to illustrate some of them and leave you with pondering what you think about it. This is the beauty of what we're facing today. from perspective of a couple of decades, is almost unimaginable. This is actually a meshing of two data sets, subsets of the two data sets, at frequencies which are most fruitful for direct CMB analysis. So we're seeing two WMAP frequencies, V and W, which were the primary vehicle for cosmology analysis in the final results of WMAP, mixed with 3 from 2 instruments from Planck, 70 and 100 and 143, and expanded version of what Charles showed you on a couple of frequencies, namely null tests on checking what originally was the motivation already when COBE was conceived, very nicely and succinctly put by Ray Wise in one of the papers early before COBE even flew. Why do you pay all these big bucks to go to space to do this? It's this large-scale stability, complete nulling of CMB anisotropy between any pairs of these maps, even between different instruments, between different satellites. So that's exquisite, and I included the 143 to whet your appetite, to just start showing how much foregrounds are picking up. This is our best frequency in sensitivity, but already foreground is here, bigger than, larger in amplitude than elsewhere. So this is the playing field. What do you with this? What do you do with this on large scales? How does it help us further the questions that were pointed before? Well, to take the bull by the horns, let me immediately show for, if you can retain some visual recollection of this would be useful. This is 100 gigahertz map. God, this is this complicated. At the bottom here, this is the cleaned component separated map that represents CMB, not the one that's shown a lot. I, on purpose, picked up one which still shows galactic residuals, so you can orient yourself where you are on the sky. And then Molvide projection isn't easy to read for people, so some effects on the sky morphologically are identified as curious. Where they are located in the sky is over this area of the sky, where if you zoom on particular direction, that various analysis methods point out and project orthographically on top of it from the top of the sphere. That's what you see. And the antipodal view of that around somewhere in between galactic center and Cygnus, a little bit up, centered here, is that hemisphere. And just a simple summary of what some people see in that is much more structure, measured in various ways in this segment of the sky compared to this one, and the rest is whether you should be excited about that or not. So let's see. This is the mother of WMAP anomalies, published immediately by Tegmark and Angelica de Oliveira Costa, just, I don't know, 3 minutes after WMAP data came out in 2003. So there, I mean, this is derived from Planck data, but derived from WMAP data, it simply pointed out that the quadrupole and octopole on the sky have particular structure, which is described sometimes as the one with high orbital number, or planar, and that characteristic axis is definable in these two multipoles case, and they almost coincide on the sky. In order to prove, I'm showing that only to prove to you that I'm not an anomalies freak who wants to rub anomalies into you all the time. This is the one we give up. On Planck, these multipoles drive away from one another much more than in WMAP. It's not particularly statistically remarkable to get fixated on it. It's not really that exciting. This is only very few degrees of freedom, 5 and 7 to multipoles, so that's not the most exciting part of the story. More exciting part was visible in what George was showing at Lowell, but both from COBE, WMAP, and Planck, we're seeing this repetitive signature of somewhat low amplitude at low end of the power spectrum, low L end of the power spectrum. And there is a significant crowd of people who were inspired to try to pursue this subject by importing deviations from Friedman, Robertson, Walker, infinite homogeneous isotropic background spaces as alternatives for what universes at large scales, where there is very little other constraints on it. So typical examples exploited in that paper on topology are some models which are toroidal in nature, or basically built on tessellation on space with possibly identification of opposite faces and so forth. building on, depending on curvature of the space, on different tessellation from which you start. Or alternatively, explicitly anisotropic models like Bianchi, which are infinite, have normal hypersurfaces of positive or negative curvature, but are expanding anisotropically. They were used historically in cosmology for various reasons. Some of these are discussed in these papers. There will be a talk by Jason McEwen about Bianchi, and I will show something later on about that as well. So I will not spend time on that now. On compact topological spaces, all I'm going to say is an illustration of non-trivial correlation structure generated in these spaces. So this plot shows on top homogeneous ordinary space we're used to, Friedman, Robertson, Walker, lambda cosmology. One particular situation, you look at the pixel which is on the North Pole on this map, and you draw the correlation function with every other pixel on the sky. That's simply high correlation close to 0, going negative and slightly positive at the antipode. In compact spaces, two things emerge. There are correlations which are non-trivial in distance and non-trivial in angle, and you can compute them given the geometric model of the space. That helps you structure your analysis along the most desirable lines of building the whole correlation structure into Bayesian framework of fitting data against such models and trying to see what comes out. And what comes out is no detection of such models. What varies on this plot from top to bottom is the characteristic scale of the cell that defines such a geometry. What's shown in this row is that size corresponding to the size of the last scatter volume of the universe, the diameter of it. And then going downward, these spaces get smaller. So essentially, with topological identification of opposite faces, photons move through, cycle through, and you see the same things several times on the sky in such space. You don't detect these features in the sky. It's a minor industry of excellent mathematical exercise, very elegant. Less elegant is this whole suite, that's the old plot, whole suite of morphological attempts at looking at the data. This is an extract from the paper that Christine Mikkelsen will be discussing in a couple of days. It's been motivated by discussion early on between one of the groups trying to look for deviations from isotropy in WMAP data, and then suggestion being weaved into one of the WMAP papers about considering statistically isotropic temperature field on the sphere modified by just a multiplying function of sinusoidal nature around the direction. So here, there are some likelihood cuts on overall spectrum with the slope and amplitude on top, and amplitude of the sinusoidal modulation, the whole global field on the sphere. You have to fit for two angles for direction. I'll just point out that that's that region of the sky where this sort of fit on modulated temperature field returns significant results from WMAP, and Planck is consistent. Morphologically, there is something perhaps interesting going on when you split sky into hemispheres. Here is an example of ecliptic one with multiple point correlation function evaluation from 2 to collapse, from 2 to collapse 3, equilateral 3 and 4 point function, split between two ecliptic hemispheres. And in fact, what this plot is supposed to impress you with is not really the red curves that are going shapely through the simulated gray bands of isotropic model simulations, but the fact that on one hemisphere things are so quiet, okay, and just kind of abnormally sitting on 0. So there is a difference morphologically between how these low order correlations at order higher than 2 are sensing something on the sky. That contributes to building up this notion that maybe we're looking at something interesting. And then one interesting story weaved into this that continued through several years is that original morphological statistics applied to WMAP have been countered by more elegant approach developed mostly under Tarun Suradeep's efforts. His student Amir Hajian has been doing that penetrated into WMAP workload at some level. And we have disagreed. So some of the morphological statistics of less elegant nature were pointing to intriguing features on the sky. These guys were claiming, no, everything's isotropic. So, well, we've put some effort into merging things. We drew Tarun into Planck. He's here. He will talk about technical details of that in a couple of days. So If you're interested in bipolar spherical harmonics, listen to his talk. Bipolar spherical harmonics are yet higher order elegant mathematical framework within which you can do analysis. These are natural functions to represent such objects which are depending on two vectors on the sphere, pointing to the sphere rather than one, as standard spherical harmonics support the basis for. And you can study through them couplings in non-trivial sense on functions which are not statistically isotropic. I will only leave you here with the notion that expanded through harmonic space, there is a detection on dipolar modulation that's significant through this framework, which is very different from everything discussed elsewhere. And it also more generally allows to slice it through harmonic space into its harmonic content as a modulating field. So compared to that multiplication overall on the whole temperature map on the sky, this allows us to start limiting the content to large scales of that, imposing L dependence on possibly morphological description of something that might be acting on a sphere if we care to believe in all of that. That's an interesting point because these were two different conflicting environments which now converged looking at Planck data. Finally, the illustration on the Bianchi conundrum. I'm not sure if I'll be able to do that on this device. So here is a inept flipping demonstration. Oh, God. You're supposed to see that on the south or on the bottom and to the right, things are changing as I'm flipping the screen. And it's a manifestation of the fact that the real CMB sky has these features that I pointed out to you. And to many people looks different on that side versus that side of the sky. Now, the surprise that emerged a long time ago, again, in the context of WMAP data already, and is now repeated and is consistent with Planck, is that this sort of feature, that is a mathematical construct derived from a Bianchi model with particular parameters, which are very non-trivially actually fit against the data. So here you have a multi-parameter family of models to generate something like that. 3 parameters you lose immediately on finding the direction on the sky and rotation around it. And then you need a few parameters to describe the density, the shear, and vorticity in this model. I'll spare you the description of the physics of it. It's intriguing and interestingly curious from general relativistic point of view. Bianchi models generate such features in completely homogeneous universe without perturbations. And there's a long history of weaving this into various ways of thinking about cosmology at very large scales before inflation happened. It fits the data very well. On every parameter, it's significant. And when you remove this function divided by a factor of 10 in color here, because it's amplified from real sky, it produces manifestly more isotropic rendition of the sky. What does it mean? Well, nothing particularly good, because this model is seriously open. It cannot be meshed in the framework of inflationary or whatever flat cosmology with lambda. It just simply doesn't fit. There was an effort made before to expand on this. We had a paper where we tried to put lambda to work with this model, keep attributes of lambda cosmology, but give it lambda and make it flat. It's a little tedious because it becomes non-analytical. You have to integrate numerically, but that was studied, described in literature by various authors. It ruins things, it doesn't work. So this is not a physical basis for building cosmology, unfortunately. It's tantalizing because the non-trivial nature of this pattern and the fact that it fits the data, who knows, maybe it tells us something. Maybe not, it's a curiosity. Situation is excellent, but not yet hopeless, as some joke. Fortunately, people are willing to help. We have Jens Kluba in the room, so you can ask him what is the list of propositions they made 3 days ago on AstroPH of how to address this situation. All of that is quotes from their paper, which just appeared. There are always candidates for handling explanations to phenomena of the nature that I described. if you care to believe in them. There were more described in the isotropy and statistics paper. I obviously don't have time to go through them. Go to the session. Christoph Reth will talk about phase correlations. Some other people will talk about other stuff. This paper, interestingly, argues that there is future in temperature and temperature polarization and EE correlations, discerning on some of proposed mechanisms that might be operating, generating such oddities. And I'll stop here on Escher and his sphere and leave you to serious numbers.
Questions?
Chris, one of the things we've heard most about is the low quadrupole, yet the Planck quadrupole is higher than WMAPS.
Yes.
Can you say why that is?
Because we're probably better on component separation. Yes, I might return the volley and ask you, so how is it that from 7 years to 9, you dropped the quadruple by a factor of almost 3?
I think that was just the optimal CL I think that was just the optimal CL estimator that did that. And
Right.
I would say the reason your quadrupole is higher is probably because you used more of the sky.
Right. So yes, I think, personally, I like low L's a lot. You've seen some illustration of how much action is there. I think that whole thing has to be revisited through common, as unified solution attempts as possible. So if you're an accuracy freak, I would argue, I tried to do some of that myself. It's not easy with your data. The WMAP data were released at pixel resolution, which is a little poor. The one that comes closer to Planck is unwieldy because it's split differential assemblies and so forth in years, so you have a lot of things to grind through. It would be really nice to have NSI 1024 maps to directly do the work, I think. But we can discuss the technicalities of that later. Then we can set up frameworks of really going identical on sky coverage, on component separation. There's a lot of them. Your question is very rich. As you know, V and W bands to do cosmology with template-corrected foregrounds, very different from what we're doing. Our degree of confidence in component separation is not a matter of a joke. We're using 4 methods which are rather different from one another, and we're deriving rather consistent CMB solutions at the regime where we talk about things like quadrupole on the sky or first 30 multipole. So we're not here on a shifting sand from our end. That's something to be taken very seriously and synchronized. I believe that joint WMAP Planck data set will be with us for several decades as something exemplary to do cosmology with. So I'm looking forward to standardizing that and having a common answer.
Another question?
Chris, did you try anisotropic dark energy models? For instance, you can have something like pressure is equal minus energy density on diagonal, but there will be 10% of all diagonal component of the energy momentum tensor. You can in principle arrange it using many vector fields, so you didn't try this.
Well, obviously, personally, I didn't, because I was more like subtracting some maps from some other maps.
Yeah, but
there are other people. Data is now publicly released, and it's really good if the microcosm of cosmologists sink their teeth in them and do that. I would encourage that. I did it.
No, but somebody did it. Okay, it contradicts.
Not amongst us, no, I don't think so. That paper is already pretty thick and big, but it doesn't have that in it yet.
Any other question? If not, then let's thank Chris again.